Okay, so welcome to Lab 1, everybody. What we're going to do in this lab is I'm going to introduce you to our materials testing system, and we're going to do a couple of tests of different materials. So here's our materials testing system. It's an electromechanical system built by the MTS company. And it's got a couple of different grips. The lower grip here is fixed to the base of the instrument. The upper grip is attached to the crosshead, which moves up and down. And that's computer controlled over there with our PC. And in between the upper grip and the crosshead in series is a load cell, and that's a force transducer. So that records the force that is being applied to a sample positioned in between the grips as the crosshead moves upwards for a tensile test or downwards for a compressive or bending test. Now, for elongation of the sample, which we'd need to calculate stress and strain and produce a stress-strain curve, what's used is this little device called an extensometer. So it's a really sensitive device, and what it does is it has two knife edges right on the ends there that get physically attached to the sample that's being tested using these little spring clips. So these little spring clips just go around your sample and secure the knife edges onto the sample. And the extensometer starts on the sample with its arms closed at the start of the test. And there's a physical stop here on the extensometer so that you know when the extensometer is fully closed, the distance between these two knife edges is 25.00 millimeters. And as the sample elongates during the test, the arms of the extensometer separate, and that separation is recorded. And that separation is equal to the amount of elongation that the sample experienced between those two knife edges. During the test, the extension data from the extensometer and the force data from the load cell are transmitted and streamed to the computer where they're saved in a data file. So the data file that we're going to get out of each test has force data, elongation data, and we'll also record the time too. So there are all of those data columns that you're going to get in the test files for these different samples. So let's take a look at the different samples that we're going to test today. Okay, so here are the three different test samples that we're going to test in today's lab. The first one's a sample of A1011 structural steel that's very similar in material properties to the A36 steel in your material property tables. And the second two samples are both made out of PLA plastic that's being printed with our Dremel 3D printers here in the lab. Now, the shape of these tensile samples is described as a dog bone shape, and the reason for that is that the wider portions at the top and the bottom are where the samples are gripped for mechanical testing. And the compression force that's caused by the grips tightening against them induces some additional stresses that you don't want to be confused or you don't want to have compounded into the results of the tensile stresses that are being created during your test. So the actual area where the measurements are made for the stress that the sample is experiencing is throughout this center region that's called the gauge region of the sample. And within this central region, that's far enough removed from the spot where the sample is going to be gripped and compressed that our lines of internal force transmission throughout this central region are all going to be nice and parallel to one another and aligned longitudinally with the sample's axis. So in order to calculate stress from the force that's being applied to the samples, we need to know what the width of each sample is, so the measurement across here, and also what the thickness of each sample is, and that gives you the cross-sectional area of the gauge region. So what I'm going to do is I'm just going to use my calipers to measure what the width and thickness of each one of these three samples is, and then I'll write them down here at the bottom. Okay, so I've made the measurements of the width and thickness of each of our three samples, and you can see them written down there. So for the structural steel, width 5.90 millimeters, thickness 2.96 millimeters. For the first PLA sample, second sample out of the three, we have a width 10.18 millimeters and a thickness 3.12 millimeters. And then for our third sample, also PLA, we have a width of 10.20 millimeters and a thickness of 2.98 millimeters. So I'll get the first sample now. So we're going to do the structural steel first. So I'll mount that in the material testing system, and then we can start our test. Okay, so I've got our first sample here, the structural steel, and what I'm going to do now is mount this in the material testing system. So the first thing I'm going to do is mount it in the bottom fixed grip here, and I'm just making sure that it's positioned in the center and getting it set so it's vertically straight. Okay, and then I'm going to tighten this lower grip up and straighten it slightly. Perfect. Now I'm going to carefully put on the extensometer, and I'll show you, I'll give you a close-up of what this looks like after I get it on. But I'm squeezing together the arms just lightly to make sure they're fully closed. And there we go, the bottom knife edge is clipped on now, and the top knife edge is also clipped on. So the extensometer's attached now. Now the sample at this point is under zero load and it's zero elongation. So what I want to do is I want to go over to the computer terminal and just zero the force on the load cell and zero the displacement of the extensometer. So do that. So zero load and zero extension. Okay, so now we've got zero load, zero extension. Now I'm going to make sure that the top clamp is opened up, and I'm going to lower the system, the crosshead down. Okay, there we go. And then I'm going to tighten the top grip up. There we go. Okay, you may be able to see over here now that when I tighten that clamp up, there's a significant load that's being applied, right? So here I've loosened the clamp again. Now I'm going to tighten the clamp up, and there we go. So just by clamping it, we've extended the sample up slightly because of the way these grips are designed, but that's okay because that load now that we've induced by tightening up the clamps is captured as our starting load, and the extension that's being recorded is captured as our starting extension as well. So here's a close-up look at what that extensometer looks like attached to our sample. So you can see the clips that are holding it in place, and the knife edges on the back here that clip to the sample. So as these arms of the extensometer separate, it'll record the extension between these two knife edges that are initially separated by a distance of 25.00 millimeters. Okay, so we're all set up here now. We've got our sample fixed in place and we're ready to begin this test. So I'll hit the play button and the crosshead will start moving up here on the system and we'll get a live graph that develops of force that's being applied to the sample versus elongation of those extensometer arms, or separation of the extensometer arms, which is elongation of the sample between the arms. So here we go. Okay, so our test is now running and we're in the linear portion of the curve, so you can see a nice linear line between force and extension there. And now the curve is flattening out, so the sample is yielded, and now the curve is completely horizontal, which means the sample is elongating continuously with no additional applied force. And now we're in the strain hardening region of the curve, where load is increasing again with applied extension. And you can see down on the x-axis the amount that the sample has elongated by between the arms of the extensometer and the load that's being applied on the y-axis. So now we're up at about 6.4 kilonewtons now. So a significant amount of force being applied here. And as this curve continues to develop and the graph auto scales, you'll get an appreciation of just how small the elastic region of the curve is in terms of the steel's overall extensibility. Okay, so you can see that the slope is becoming increasingly flat, so we're approaching the ultimate strength of the sample here. And as soon as the curve begins to decrease in force, you should see a point of focal deformation in the sample develop. And that's the necking region within the sample where all the extension is going to be concentrated. And the development of that coincides with the beginning of the necking region of the stress-strain curve. So let's look for where that necking region is that develops. Okay, it should be visible here soon. And you can start to see a focal decrease in width occurring right about there. That's where all of the elongation in the sample is now being concentrated. So overall, on our force deformation curve, the force is going down, but the actual material within this region is becoming stronger, even though the sample is able to withstand less and less force. And you'd see that if you were to plot a true stress-strain curve, which would require measuring the cross-sectional area at this location continuously throughout the test. Okay, the test is paused here, and that's because the extensometer has a maximum deflection of 10 millimeters. So I'm going to remove the extensometer here. Okay, there we go. And now we'll start the test running again and let the sample fracture. So you won't see any displacement anymore on our curve. So there we go. So the sample's broken now. So that finishes up the test of the steel sample. So I'll save that data and then I'll get the first PLA sample mounted up and we'll do that test. Okay, so we've got our first PLA sample all set up here, ready to go. So we'll start the crosshead moving and see what the force elongation curve looks like for this sample as it develops. So here we go, starting the test. All right, so nice linear response there between load and elongation. So the material really does behave like a spring in this region, F equals kx, or if you normalize those values to the dimensions of the sample, stress and strain, or stress equals modulus times strain. Now the curve is becoming a little bit non-linear. And decreasing in force carrying capacity now, and we should be seeing fracture sometime soon. Okay, so good fracture near the center of the sample there is what we'd sort of expect. Okay, so now we're ready to test our third and final sample, our second PLA sample. So let's start the crosshead going, and we'll again see how the force elongation curve develops for this sample. Okay, nice linear response between applied force and elongation there. Up at a little over a kilonewton of applied force. And the curve is decreasing in slope. Okay, and fracture. So we'll stop that test there and save the data.